All right. This is going to be an Aspen tutorial to size a distillation column for the distillation lab report for lab. So when you do an Aspen file, you're going to have these four things down here: properties, simulation, safety analysis, and energy analysis. For the sake of simplicity for this class and for designing, you're just going to be using properties and simulation. So when we start in simulation, there's two folders here that are labeled in red, and that means that's got to be something that we initialize. So when we start, we're going to start in components right here, and we're going to have specifications. We have to specify the components we're going to be using. So for this lab, we're going to be using ethanol and water. So we have to go ahead and find those. And when you're searching for them, click equals. This makes it easier to find, and you don't have a long list of chemicals down here to sort through, because sometimes it'll just bury the one you're looking for in a bunch of other ones that you don't need. So we'll do equals, and we'll type in ethanol. And then here it is. Add selected compound. All right, and then we're gonna find water. And we're gonna add selected compound. And it's gonna come up with this. Just click add. You're not gonna take anything out or anything else in. So we have our two components. So now we can go down to methods. And we're going to click the folder down, and we're going to see that specifications has to be specified. So we'll go there. And this is where we're going to be putting in the methods that we're going to be using for sizing and for thermodynamic behaviors. So I already solved that, used the method assistant to help me find the right method to use for this. So what we're going to do is we're going to go to base method, and we're going to scroll down, and we're going to use NRTL. And then something else to add on to this, if you're going to use NRTL, you have to go down to free water method and change this from Steam TA to Steam NBS. If you don't change this to Steam NBS, you're going to end up with errors. But when this happens, you see that there's parameters down here. That's in red. So go ahead and click that down. And this is going to be for binary interaction. So we're just going to click that. And it's going to come in blue. That's just what happens when you do this. It helps specify more interactions that happen throughout the simulation. All right, so now when we close these folders, we're going to see that everything that we need to initialize is initialized. So we're done with the properties tab. So now we're going to go to simulation. Now here's where we're going to be doing all of the streams and blocks and columns. This is where it all happens. So you remember from the problem statement, we're going to start with our first stream. And when you do this, press material to bring up a stream, drag it out, left click, and then press escape. If you don't press escape when you put in your stream, it's going to keep adding in more streams, and you're going to have to keep deleting them. It's just going to fill up your simulation with a lot of things that you're going to have a hard time keeping track of. So we'll go to stream 1. And so for this, we have to give the temperature, the pressure, the flow rate, and then the compositions of our components in the stream. So for this, I'm just going to use one of the temperatures that was used for the column to heat the ethanol and move up through the stages. I'm just going to say about 200 degrees, because when you look at the vapor liquid equilibrium chart for water and ethanol, you start to notice more boiling around 190 up to 210 degrees. So I'm just going to go in the middle, use 200. I would recommend using one of the temperatures you observed in your experiment. But if you don't remember, or if you don't have good results, if you use it, just go ahead and use 200 degrees Fahrenheit. And we're going to run this at 1 bar. We're assuming it's coming in with atmospheric pressure. We're assuming we're not pressurizing this at all. And we're going to have this come in as a mass flow, because remember, the flow rate we were given to start was 200,000 kilograms per day. So just make sure your units are right when you do this. If you have it in hours, just make sure you convert from days to hours. And the compositions that it gave us to start off were 10% ethanol and 90% water by volume. So if you want to use a volume percent, go up to composition and go to standard volume fraction. All right, so there's going to be no units because it's a percentage. And for this, you're going to do 0.1 at ethanol and then 0.9 for water. All right, so now this stream is completely initialized. We gave it everything it wanted to know. So we're going to go back to our main flow sheet. And so something that I like to do whenever I'm designing something in Aspen. So for most of the stuff that you will design in Aspen, you're going to have to use two different blocks of the same kind. You're going to need one type of heat exchanger and another type to size a heat exchanger. You're going to need it for a distillation tower. You're going to need it for other things. So you're going to have to use this stream, your entering stream, more than once. So to make your life a little easier, you're going to come down to manipulators. You're going to go to the second block here that says DUPL. That's a duplicator. You're going to click it on the flow sheet, then press escape. And then you're going to go to your stream, right-click it, come down to reconnect, and click reconnect destination, and connect this stream to the duplicator. So now, anytime you have something coming out of this duplicator, it's going to duplicate the stream that goes into it. So if I have, let's say, 2 streams coming out of here, I'm just going to put in 1 for now because that's all we need. But if I bring another stream coming out, stream 2 and the next stream are going to equal this one here. All right, so like I said before, when you're sizing a distillation column, you're going to need 2 different types. So what Dr. Mubin liked to call this was the shortcut method and then the long way. So we're going to start off with the shortcut method. So for this, since we're going to be sizing distillation columns, we want to come down to columns right here. And the first one we're going to use is the DSTWU. It's going to be the first one down here all the way to the left. Let's go ahead and click it. And then click on the flow sheet where you want it to go. Press escape. And now we want this stream here, which is technically also our stream 1, to enter that column. So we're going to press reconnect, reconnect destination, and then connect it to the DSTWU. And then for the sake of simplicity, I'm just going to label this DSTWU, just so that I know which distillation column this is. All right, but now we have streams coming in, and we also have to bring in streams coming out. So you're going to click material, and you're going to bring in streams where there are red arrows. This means that these are required streams for the block. So we're going to have our distillate, and we're going to have our bottoms. All right, so now we have a new block in here that we have to specify. So if you go over to blocks on the left-hand side where all the folders are, press the arrow to the left to bring the folder down. Go to DSTWU, which is this block right here. Click it down. You see that input is in red. So we have to initialize the inputs that we need for this block. So this is what's going to come up. And for the sake of simplicity, you're going to make your condenser and your reboiler 1 bar. Now, in the lab, this is not running at atmospheric pressure, but for the sake of not getting errors and constantly having to work through different sensitivity analyses to figure out what your pressure should be, just make them both 1 bar. All right, and then for column specifications, we're going to be determining these 2 things right here, number of stages and reflux ratio. We're going to be figuring this out, but I will get to how to solve for that here in a second. So for now, in order to get this column to run, I'm going to specify the reflux ratio. So I'm going to click in and fill in the little dot next to reflux ratio so I can actually input a number. I'm going to put in 50. Now, this is a really big reflux ratio. For a lot of things that you design, you're never going to have a reflux ratio this big. But when you're sizing a distillation column like this in Aspen, when you're trying to design it, you want to use a bigger reflux ratio just so that when you actually figure out what your reflux ratio is, you can actually run this simulation so that it's not below the minimum reflux ratio. If you run this below the minimum reflux ratio, you're not going to get any results and you're going to end up with errors. So for now, just make that 50. And then you're going to go to your key component recoveries. So for this, with this, since there's only two components, this is really easy to do. We have our light key and our heavy key components. So our light key component is going to be the most volatile substance in this mixture. It's going to be the substance with the lowest boiling point, which in this case is ethanol. So when you go down to comp, you're going to click the arrow down. You're going to go to ethanol. You're going to click that, and that makes your heavy key, in this case, water. And so the problem statement states that you should have 85% by volume ethanol in your distillate, but you may not get that for this, and that's okay. As long as you have at least 85% recovery in your distillate, you're fine. So I'm not going to go into depth about recovery. You're going to learn more about that in your design class. But for now, for the sake of it, put in 0.085. This means you want to try to have 85% recovery of ethanol in the distillate. Next is your heavy key. And when I tried running this, and if I did anything above 0.01, I kept getting errors. So for the sake of simplicity and for the sake of not wasting time, make it 0.01. So I'm going to save. And I recommend saving pretty much every time you input a number. Aspen has a tendency to crash at the least convenient times. I recommend just constantly saving. That way you don't lose anything that you put in. All right. So now we have a blue check mark up here. That means everything on this page is initialized. And we also have a blue check mark on the left side here for the actual block itself, meaning everything that is needed is initialized. We could run this, but there's something else that we want to do. And this is going to help us determine the number of stages and the reflux ratio for the distillation column. So on this page, if you stay at the input of the DSTWU, you're going to go to calculation options, and then you're going to click on generate table of reflux ratio versus number of theoretical stages. What this is going to do is when you run this, you're going to get a table, and you're also going to be shown how to make a graph of the reflux ratio versus the theoretical number of stages. And this is going to help you make a decision on how you want to run this. But you want to initialize the number of stages and give a final number as well. So I'm going to give 1 to 100. All right, so now everything is put in. And so now I'm going to save. And then I'm going to run it. All right, so now results are available. I'm going to check to see the stream results of the DSTWU. And how you do that is you're going to go and right click. You're going to go down to stream results. And it's going to give you all your specifications you need for each stream that's entering in and leaving the distillation column. You're going to be able to use this to find your mass flows, your fractions, and you're going to be able to figure out your compositions and concentrations of all your components within here to determine how well you separate it. All right. You're going to go to main flow sheet. You're going to right click on the distillation column again, the DSTWU, and go to results. All right, so we have our minimum reflux ratio of 8.15. We gave a reflux ratio of 50. So that means it was able to run all right. If we put anything under 8.15 as a reflux ratio, this wouldn't have run. So we're going to go to reflux ratio profile. And it's got this table here that compares reflux ratio and theoretical number of stages. So this would be, all right, I have this many stages, and this is what the reflux ratio would be over here. So left to right. But in order to see this a little better, you can make a graph of this. Now you're going to do this is once you're on this page and you have the table, go to the top right of the screen and you're going to see custom up here. You're going to press that. And it's going to give you a chance for you to select your x-axis and your y-axis. It already gave us the x-axis is going to be the theoretical stages. You're going to want to select reflux ratio for the y-axis. You're going to press OK. And here's a graph that's going to show you your theoretical stages and what the reflux ratio would be at those stages. All right, so when you observe this graph, you're going to make a decision, and it's going to be based off of how much reflux do you want and how many stages are you willing to put in. When you have a graph like this, I recommend going close to where the plot levels off, because that's usually going to be your optimal decision conditions. Excuse me. So I'm going to choose 24 for the stages and 8.86 for the reflux ratio. All right. So to make things a little easier for when we start the long way method, I'm going to change this. I'm going to go put in the number of stages instead and make it 24. I'm going to run this again. Okay, you're going to go back to your main flow sheet. You're going to go to results by right-clicking on the block right here. You're going to go back to summary. All right, so we have our actual reflux ratio of 8.85. We have our actual number of stages, 24. We have our feed stage, meaning this is feeding above stage 23. And we also have a distillate to feed fraction. We're going to need this later on. All right, so now our shortcut method is done. Now we have to actually make a long method so that we can actually get a diameter and a height for the column. So we're actually going to get our sizes, and we're also going to be able to get our condenser and reboiler duties to figure out how much heat is moving through. And this is why I like using the duplicator. So now I can just get a product stream moving out of the duplicator, and it's going to be the same as the first stream we started out with, the conditions given by the problem statement. So now we're going to want to use a different column from the DSTWU. We're going to want to use, if we go down here and we're on columns, the third one here on the left side is the radfrac. That's the one we want. So we're going to click on that. We're going to click on the flow sheet, press escape. I'm going to move this down a little bit, give both blocks a little bit more space. Here's the name over here. I'm going to label this radfrac. You're going to right click on stream 5 in this case, which is the stream that's going to be, which is the second stream coming out of the duplicator. You're going to go to reconnect destination, and go to feed. All right, and then we go to material. We're going to do liquid distillate because that is the distillate we had in the distillate collector on the actual column that we were using in lab. And then we're going to put in outgoing streams for the distillate and the bottoms. All right, so now we have a new block again. I'm going to save really quick just to make sure I don't lose anything if anything crashes. So we have a new block, and now we have to actually put in conditions for it. So I'm going to right click down. I'm going to go to specifications. I'm going to go to setup. All right, so now this is where we're going to be putting in a lot of the things that we found from the shortcut method. So our calculation type, we're going to leave that in equilibrium. We don't want to mess with this. We have our number of stages. I chose 24. Our condenser is a total condenser. And now we have operating specifications. We have our reflux ratio. If we go back to our DSTW results, for the sake of simplicity, I'm just going to copy and paste it. So you're going to hover over the value, copy, go back to radfrac, and then paste it. And then something else we're going to use the distillate to feed ratio. We're using these because these actually came from the results tab of the DSTWU. We're going to have something that's more accurate to what we already made. So I'm going to go back to the DSTW results. Then I'm going to go to distillate to feed fraction. I'm going to copy and paste that value over. All right, so now this configuration part is done. So now we're going to go to streams because that's in red, and that's something we have to initialize. And here is just where we're going to specify the feed stage. So if you remember from the DSTWU results, we fed above stage 23. And that's all we have to do here. It's that simple. All right, and then for pressure, we didn't run technically at atmospheric pressure because it was technically a closed system. But for the sake of simplicity, and since there really wasn't much pressure change observed throughout any of the experiments, make the top stage 1 bar, and then that's it. I'm going to save. Then I'm going to run it. All right, results are available. So that means we were able to run this column without any errors. So that means we initialized everything and nothing was out of place. So to double check your separation, go down to your rad frac. You're going to right click it, and you're going to go to stream results. And like I said before with the DSTWU, this is where you're going to verify your flow rates and your compositions of your streams. And again, like I said, as long as your distillate is at least 85% ethanol and your bottoms is mostly water, it's okay. It's okay if you're not on like completely on par with the specification set. As long as you have something that works and separates mostly ethanol in the distillate and mostly water in the bottoms, you'll be set. All right, so now we actually have to size this column because we need the height and the diameter. So for this, it's actually going to be pretty easy. You're going to go to the radfrac folder in blocks on the left-hand side here. And then you're going to go to this third folder right below it, column internals. You click that. Then you're going to add new. This is going to come up with missing hydraulic data. So all you have to do for this is generate it. Aspen's going to do it for you. There's nothing new that you have to do for it. All right, and you're going to double click on INT1, and it's going to bring you here. All right, and then for this, you're going to do auto section. You're going to base it on flows. Okay. And then you're going to run it again. But first, I'm going to save. And then I'm going to run it. All right, so once we've run it, we can view internal summary right here. And now we have our height over here. We have our diameter down here. And then, so now we have our sizes. So now we need the condenser loads and then other specifications of the column. You can right click on the radfrac and go to results. And it's going to give you everything else that you need. It's going to give you your heat duties for your condensers and your reboiler, and it's going to give you the other things that you will need. All right. That should be it for the tutorial. And yeah, follow this, and you should be able to have a size distillation column with close enough parameters to what was set by the problem statement. If there's any questions, please feel free to reach out to me or to your design TA or to your design professor to clear up any confusion. And yeah, thank you for watching, and good luck. Thank you.